This lesson is on the Hinge theorem. And to do it, we're going to use two boards here, the screen door board, and we're going to use the door. Okay, let's observe some things about the door here. The door has a width, which we'll use in a moment to be the side of a triangle, and then the door frame, the black up here at the top, that's going to be the other side of our triangle. So what we'll do, we'll open it up, and we'll notice that when we open it up, the door does not change the width. No. The door stays the same. It's congruent when it's at this location, and when it's at this location, it's the same size. The door frame, the black at the top, does not change at all. It's congruent no matter what I do with the door. First thing I'm going to do is make a triangle. Okay. I've got the door frame is one side of the triangle, the door is the side of the triangle, and then this piece of screen door board, which is what you use to nail screen onto a door so the mosquitoes don't get in, this screen door board will come here and be our third side of our triangle. So here we have the door frame, the door, and a piece of screen door board. They make a triangle. Okay. Second off, I will open the door wider so that now I have the door frame being one side of the triangle, the door being one side of the triangle, and now a longer screen door board being the third side. So the door is congruent in this triangle to it was the previous one. The door frame is congruent to the one in the previous. The only thing different for the sides is the third side, which now makes a triangle. So we notice from that we have two triangles that have two congruent sides. The two congruent sides are joined here at this handy-dandy device known as a hinge. So here we have the hinge joining the two congruent sides in both of the triangles. Well, let's look at that again. Let's notice when I open the door up, the door stays the same, the door frame stays the same. I put the big piece of screen door board on it, and I look. I've got a big piece of screen door board and a big angle. Who would have thought? Then if I use the little piece of screen door board, now I've got a short third side and a small angle, and the small angle is over there where the handy-dandy division, the hinge, is located. So we're going to have two different triangles, one with the door open a little bit, one with the door open a lot. In both of the triangles, the door is congruent to the door frame is congruent to the door frame, and they are connected at the handy-dandy division, the hinge. So that's what you need to know about it. And we'll see how that applies here to our geometry. It is, in fact, the Hinge theorem, which we have right here for us. So, the Hinge theorem. If two sides are congruent, two sides of a triangle are congruent, and the included side is larger, then the third side is longer. When using the hinge theorem, you're going to need to always be aware of where the hinge is, because that's going to be one of the crucial elements. So we have two sides that are congruent, and they are connected at the angle in question, which is opposite to the two sides that vary in length. Also, the hinge theorem converse. One goes from angles to sides, the other goes from sides to angles. Notice in using the hinge theorem, the difference between the previous theorem, the long side big angle, here's the long side big angle and the hinge. The long side big angle is within one triangle. So we use the long side big angle when we're inside of one triangle. It's relationships of the sides and angles of one particular triangle. The hinge theorem, on the other hand, is comparing two triangles that have certain characteristics in common. That being, two congruent sets of sides, two sides, they're congruent, joined at the hinge. Notice that these are not going to be similar, they are not going to be congruent, they're not going to be any of that kind of stuff. There's not going to be any proportions that can be made, generally speaking. It's two congruent sides joined at the hinge, and we make inequality statements about the other side or in the converse about the angle. So what does that look like? Here we have an example. We ask, does the Hinge theorem apply? We've got two sides that are congruent, the marked sides and the common side. So yes, there are two sets of congruent sides, and they are joined at the angle in question, the hinge. So it does apply. Since the angle 36 is bigger than the angle 2, then AD is bigger than DC. Look at this example. Does the Hinge theorem apply here? Well, we have congruent sides. We have the common side that's congruent, and they are joined by the hinge angle. So here joins the orange and the purple, and here joins the orange and the purple, and that's where the hinge is. So yes, it does work. The Hinge theorem does apply. Since we know the side lengths, that can give us an inequality with regard to the angles. We'll see that since 24 is bigger than 18, then its angle, opposite, 2x plus 3, must be larger than 63, which is opposite the smaller one. Oops, there we go, which is opposite the smaller one. We can solve this out algebraically like this. 2x plus 3 is greater than 63. Thus, x has to be greater than 30. I say, well, that sounds good. X is bigger than 30. Okay, well, what if x is 200? That's bigger than 30. So then this angle would be 200 times 2 plus 3, which is 403 degrees. I'm thinking this triangle does not have an angle in it that's 403 degrees. There's got to be some limit there. You say, well, okay, this angle has got to be less than 180 or it won't be a triangle. So we need to put that additional criteria in. Here I have 180 is bigger than, or the angle in question, 2x plus 3, is smaller than 180 and greater than 83. Let's remind ourselves about solving compound inequalities. We must do the same operation to all three areas to be able to solve it. When we do that, we solve it down and we find out that the possible ranges for the value of x are between 30 and 88.5 to make a triangle here. So that's this one. We see that no individual angle can be bigger than 180 degrees. That's the one we just did. When we're dealing with the variable in the angle, that's how that will play out. Oops, sorry. When we're dealing with the variable in the angle, that's how it will play out. If the variable is in the side length, then we need to apply the triangle inequality theorem and notice that the side lengths still have to add up appropriately. So in this case, when we're working it from the from the perspective of the variable in the side, since x plus 2 belongs to the biggest angle and 24 belongs to the smaller angle, x plus 2 must be greater than 24. But notice, according to the triangle inequality theorem, x plus 2, this side,
must also be smaller than the sum of the other two sides, 18 plus 15. So our other limiting factor is the sum of the other two sides. We've found that the other two sides must be bigger than the side in question, which is bigger than the Hinge theorem side. We solve it down and we find out that the values for x in this different problem using a similar scenario is between 22 and 31. And here endeth the lesson.